Hello everyone. This video is on section 10.3 part 2 titled Logarithmic Functions and Applications. So in this video I'm going to be going over a version of the Knewton Alta assignment for section 10.3 part 2. Please understand that the questions I see in this video may not be the same questions you see when you work on the assignment on your own. But the objectives are the same and the kinds of questions you see should be similar. So I'm hoping that watching me go over these several here help you out in some way when you work on the assignment yourself. Alright, so here's the assignment page. Now you will not see the words preview of, you're just going to see the title of the assignment. Then you have your mastery bar, right, telling you how far along you've gotten in the assignment. Then your objectives. Now it looks like there are 3 objectives for this particular assignment. And then under each current objective there's a question related to it. And at the bottom of each question there should be a feedback button where you can send feedback to Knewton if you wish. You will not see the instructor cheat button, right? This will not be here. But you will see a more instruction button, right, which you can click on and get access to further reading material, maybe some videos related to the objective you're working on, and hopefully that helps. Alright, so before I get into the questions themselves, I do want to talk a bit about logarithmic functions, basic logarithmic functions. And you're going to see some similarities between basic logarithmic functions and the basic exponential functions. Or if you recall those from a previous video, from a previous assignment. Alright, so we're going to talk about basic logarithmic functions, meaning f of x or y just simply equals the logarithm base b of x, where b is a fixed number, right? B is called the base of the logarithm, right? Where b is a positive constant. Right? We're not going to look at logarithms with a negative base, okay? So b is a positive constant. Now, I'm going to do some examples of logarithmic functions. Now, hopefully you can recall from section 10.3 part 1 the relationship between logarithms and exponents. Remember that if y equals the log base b of x, that's the same meaning as b to the y equals x. Right? There was a way to go back and forth between logarithmic form and exponential form. Right. And when you're asked to evaluate, the log base b of x, you're really just finding what power do I raise the base b to get x. Alright, so my first example of a basic logarithmic function, just the log base b of x, would be f of x equals the log base 2 of x. Alright, log base 2. Okay, and then just like with any other function, I'm going to make an input-output chart, pardon me. So x and f of x, or x and y. And then what'll give me some nice outputs here are powers of 2, right? Because this is log base 2. So if I input a power of 2, this will give me a nice output. So powers of 2, so say like I plug in 8, plug in 4, plug in 2, plug in 1, just keep cutting these in half, right? 1/2, plug in 1/4, plug in 1/8, and what am I going to get? All right. Now, hopefully, again, I'm hoping you recall how to do these logarithms from section 10.3, part 1. The log base 2 of 8 would be 3 if I plug in 8 for x. And that's because 2 to the third power is 8. Right? These have the same exact meaning, one in logarithmic form, one in exponential. So the ordered pair 8, 3 will be on the graph of this logarithmic function. The log base 2 of 4 would be 2, right? Since 2 squared is 4. So input 4, output 2. Input 2, the log base 2 of 2 is 1, since 2 to the first power is 2. And the log base 2 of 1 would be 0, right? Since 2 to the 0 power is 1. So we got the point 1, 0. Then the log base 2 of 1/2 would be -1, right? 2 to the negative first. Remember that negative property, negative exponent property? 2 to the negative first is positive 1/2. Right? The negative powers are just the reciprocals of the positive ones. So I'm getting -1 here, and then the log base 2 of 1/4 would be -2, since 2 to the -2 is 1/4, and then -3 when I input 1/8, and so on. And again, I can do this all day long. Just plug in different powers of 2 for x. So if I plugged in 16, the output would be 4. If I plugged in 32, the output would be 5. If I plugged in 1/16, the output would be -4, and so on. And I'll make a quick sketch of this graph on the xy plane. Alright, and plotting these points from my chart, we get these, got 8, 3, 8 for x, 3 for y, right? 8 input, 3 output, 4 input, 2 output, so 4, 2. Then 2 input, 1 output, 1, 0. Then 1/2, -1, so half for x, -1 for y. Then 1/4 for x, -2 for y. Then 1/8 for x, halfway here, and -3 for y. And do you see what's happening? And hopefully you can see what's happening. If I start connecting these, it's very much like an exponential function. But instead of being above the x-axis, it's to the right of the y-axis. So this is going up forever that way, right? Like I said, if I plugged in 16, I'd get 4. If I plugged in 32, I'd get 5. It would just be going up very, very slowly. But then notice that the entire graph would be to the right of the y-axis. All right, the y-axis is never touched. The graph gets close to the y-axis, but never actually touches it. So if you recall horizontal asymptotes, this y-axis would be called a vertical asymptote. A vertical asymptote. Right? It's x equals 0, the y-axis. The graph gets really close to x equals 0. The further left I go, it gets closer and closer to the y-axis, but doesn't actually touch it. All right, and then some other things about this. Y equals log base 2 of x. It's what they would consider an increasing function, because as I move to the right, as the value of x increases, the output increases. So it's an increasing function from left to right. The domain is only positive numbers. And I'm going to make that note on the next page. The input of a logarithm, right, the expression inside the logarithm, can only be a positive number. You cannot take a logarithm of 0, and you cannot take logarithms of negative numbers. All right. Those aren't real. So the domain is only positive numbers. So I've got an interval notation here from 0 to infinity, but not including 0. See, only positive x's are going to be plugged in and used as x-coordinates of points on this graph. Now the range is all real numbers. Right? If you look at the y-coordinates, this is going down forever. This is going up forever, and there's no gaps in it. So every single y value is the y value of some point on this graph. So the range is all real numbers from negative infinity on the y-axis to positive infinity on the y-axis. Alright, so let's keep this stuff in mind. These are some properties of logarithms where the base is greater than 1. Right, see, this was a logarithm with a base of 2. The base is greater than 1. Now what if the base were less than 1? Alright, let me show you another example. So another example of a basic logarithmic function. Say f of x equals log, and then I'll have a base of less than 1. So instead of base 2, I'll just flip that around, make it base 1/2. Log base 1/2 of x. Alright, so again, I'll make a little input-output table, f of x. And then now this is log base 1/2, so what I'm going to do here is put in powers of 1/2. Alright, so like 1/8, 1/4, 1/2. And I'm just doubling every time now. 1, 2, 4, and 8. And you could do more, obviously. I'm just doing these 7. Now think about it. Remember what logarithms are. They're exponents. When I plug in 1/8, the log base 1/2 of 1/8, that's 3, right? Because 1/2, right, the base to the third power is 1/8. So input 1/8, output 3. And then hopefully you see where this is going. The log base 1/2 of a quarter is 2. Log base 1/2 of 1/2 is 1. The log base 1/2 of 1 is 0, right? 1/2 to the 0 power would be 1. Log base 1/2 of 2 would be -1, right? 1/2 to the negative first power would be +2. And then log base 1/2 of 4 is -2. Log base 1/2 of 8 is -3, and so on. Right? Just keep changing, going more and more powers of 1/2. All right, then I plot these points in a rough sketch on the xy axis. One. And start plotting these points. 1/8, 3. Now 1/8 would be here, comma 3, right? So really close to the y-axis. And if I went 1/16, I'd go 1/16, 4, 1/32, 5. I can get as close to 0 as I want and get bigger and bigger values of y. But I can never actually plug in 0. And again, I'll write that note up in a little bit, that you can't take logarithms of non-positive numbers. 1/4, comma 2. 1/2, comma 1, input 1/2, output 1. Input 1, output 0. Input 2, output -1. 4, -2. 8, -3. And if you follow these points, right, it looks like an exponential function, but instead of being above the x-axis, it's to the right of the y-axis. So yet again here, I have the y-axis is a vertical asymptote, right? The graph gets as close to the y-axis as you want, but never actually touches it. All right, so x equals 0 is a vertical asymptote. All right, now look at this. When the base of the logarithm was a half, log base a half of x, we have a decreasing function. Right? This would be a decreasing function. Right? As I move to the right, the value of the y is going down. Now the domain and range are the same as before. Right? The domain is only positive real numbers from 0 to infinity, but not including 0. Look at the x-coordinates, right? The only x-coordinates that can be used are positive ones to the right of the y-axis. And the range is all real numbers, right? It goes up forever, goes down forever. So the range is all real numbers. And this will be the case for any logarithm, any basic logarithmic function with a base less than 1. And my earlier example, right, these properties will be the case for any basic logarithmic function where the base is bigger than 1, right, like log base 2. Again, huge note at the bottom here. You can only input you can only take logarithms of positive numbers in this course. You'll see if you go further in mathematics that logarithms of negative numbers are imaginary or complex with an imaginary part. But we're going to stick to only having real number outputs here. So you can only take logarithms of positive numbers, right? They've got to be positive. So whatever number is inside the parentheses after the log has to be positive. And I'll put that in a little bubble. That is a huge statement, right? All right. All right, so that's also something else to keep in mind when you're talking about the domain of a function. All right, remember, 1 is you can't divide by 0, can't have a denominator of 0. 2 is you can't take even roots of negative numbers, right? Square root, fourth root, sixth root. You can't take even roots of negative numbers because those aren't real. They're imaginary. And now we can add this to that things to look out for. Right? You can only take logarithms of positive numbers. Right? So you can't have a negative number inside a logarithm. You also can't have 0 inside a logarithm. That's undefined. All right, so now I'm going to write a general statement about these basic logarithmic functions. All right. So going back to the original page here. So for f of x equals the log base b of x, if b is greater than 1, then the graph will look like this. So here's 1, and then b is greater than 1, so b would be over here on the x-axis. Then 1 over b would be less than 1. There's 1 over b, let's say, and then we got 1, negative 1. You always have the point 1, 0. Alright, the log base b of 1 will be 0. So the point 1, 0 will be on this, and the log base b of b will be 1. The log base b of 1 over b will be negative 1. And it'll look like an exponential function, but to the right of the y-axis, right? It is not touching the y-axis. Something like that. Again, the y-axis is a vertical asymptote. The graph will get as close to the y-axis as you wish, but never actually touch it. And it's going to be, when the base is bigger than 1 for these basic logarithmic functions, the graph will be increasing as you move from left to right. The domain is only positive numbers, and the range is all real numbers. And if the base is less than 1, or between 0 and 1, because remember I'm talking about only positive constant bases, then the graph will look like this. So here's 1. Now b is less than 1, so say b is here on the x-axis. And then 1 over b would be greater than 1. We got 1, negative 1. And again, you have 1, 0. Log base anything of 1 is 0. Log base b of b would be 1. Log base b of 1 over b would be negative 1. And again, it looks like an exponential function, but to the right of the y-axis. Opening like this. And again, the y-axis is a vertical asymptote. The graph will get as close to the y-axis as you wish, but not actually touch it. The domain is just positive numbers. The range is all real numbers, and it would be a decreasing graph, a decreasing function from left to right if the base is between 0 and 1, is less than 1. Okay. So now that I have the general structure of these basic logarithmic functions up for you, I want to talk about some special logarithms that you'll see on like calculators and stuff. So I'll call these special logarithms. Now, one is the log base 10 of x, or whatever. Sometimes referred to as the common logarithm. The common logarithm, base 10. The reason why it's common is because every number we usually work with is in decimal in base 10. Well, this is usually written, again, usually written, not always, but as just log. Okay. So sometimes the base will be there, but just know that if it's not, or if you see log with no base, you are going to assume that that's base 10. All right, and then the other kind of special logarithm that you'll come across, like on calculator buttons and stuff, is the log base e. Now remember, hopefully you recall from an earlier video, right? E is that number 2.71828. Right, it's 2.7 something. All right, this was E. And this was called the natural base, right? E. This log base E is referred to as the natural logarithm, right? Because E is called the natural base. Shows up in natural studies a lot. Well, Again, this, you usually won't see this. In some books I've seen this, log with the base e written like this, but and this is usually written as ln. And you'll see this a lot on calculators, ln. Now, on calculators, usually you see log for log base 10, and this ln for log base e. Right. So just please understand that you may see some special, like again, if you don't see a base on an log, it's base 10. And if you see this ln stuff, ln of x or whatever, that's the natural logarithm. That's the log base e. So please, please, please understand that. I just wanted to point those out in case you came across them. Okay, so finally, let's get into our question. We are given this function, y equals log base 10 of x, or just log of x, right? Remember, they don't have to write base 10. And that's the only one. If they don't write the base, you just assume it's 10. Alright, well, remember how I graphed earlier. My input, since this is log base 10, I'm just going to plug in powers of 10. So 1, 10, and 1/10. Alright, I'll start off with these, and those are usually pretty easy. Right. 1, 10, and 1/10. And the log base 10 of 1 would be 0. The log base 10 of 10 would be 1. So input 10, output 1. Log base 10 of 1/10 would be -1, right? Since 10 to the -1 power is 1/10. And once again, this is a basic logarithmic function, so the y-axis is a vertical asymptote. So the graph will approach the y-axis but never actually touch it, and then be like kind of like an exponential function, but all to the right of the y-axis like this. Now all we're asked to do is put in some ordered pairs, some special ordered pairs. Now if you want to see a little better drawing of this, let me show you on the Desmos website. Alright, this is that desmos.com free online graphing calculator. And if I just put in y equals log of x, see it's base 10. And you see this, remember it's a base bigger than 1, it's base 10, so you see it's an increasing function. Goes up as you go, there's 1, 0, here's 10, 1, right? 10, comma 1. 1/10, comma -1, right? 0.1, 1/10, comma -1. Those are the 3 points I plotted. And you see, it looks like it hits the y-axis, but if you zoom in closer and closer and closer, you'll eventually see that it's not actually touching the y-axis. Right, there's the y-axis here where the numbers are on there. The graph is never going to hit the y-axis. It's all to the right of the y-axis, these basic logarithmic functions. All right. But yeah, so there's a way to look at a better picture on the Desmos website. But all we're asked to do here is plug in some ordered pairs, find some points that would actually be on this graph. Well, what would have an output of 1? Now you could solve these equations, but you think, what value of x gives me a y value of 1? Well, that'd be 10 to the first, which would be 10, right? We saw that 10, comma 1 was on this graph. And what x value would give me a y value of -1? Well, that would be 10 to the -1st, or 1/10, right? And I already showed you 1/10, comma -1 would be a point on this graph. So all you're doing is plotting points or finding ordered pairs that would actually satisfy the equation. And that's all. Right. Now after every question, there should be a answer explanation, right? I would highly recommend reading over these. If you got it right, read through it to make sure you got it right for the right reasons, that you didn't just get lucky. Or they may even go over it in some alternate method that you like better and you can use for future questions. Now if you got it wrong, definitely read over the answer explanations, right? Try to figure out why you were wrong, where you went wrong, and hopefully you learn from your mistakes. Alright, next question. Alright, so this one here is on it's titled use Use logarithmic models in applications. All right. So the question is, what is the decibel level of the noise from a motorcycle with intensity 10 to the negative 2 watts per square inch? Use a logarithmic model to solve. Okay, so I'm going to pull up a formula that should have been in your reading, right, for decibel level junk, and I'll come right back when I've got that. All right, so when you click on, you can click on more instruction in the assignment or going back through your reading. You'll notice this formula brought up to you, talking about the decibel level of sound. And here's a formula relating the decibel level of sound to the intensity of that sound in watts per square meter, or watts per square inch, watts per square meter. I'll just say inch here because the problem here is watts per square inch. We have D equals 10 times the logarithm, base 10, right? Remember, there's no base here. This is that common logarithm of an I divided by 10 to the negative 12th power, where I is the sound intensity and the watts per square inch, or watts per square unit. We're given here that I equals 10 to the negative second. Right. And that's all we need. We need to fill in, that's watts per square inch. We have to fill in that for I and then solve for D, and then write the intensity or the loudness in decibels. So then D, the loudness in decibels, would be 10 times the logarithm of, and then 10 to the negative second divided by 10 to the negative 12th, right? Replacing I with 10 to the negative second. Now this would be 10 times the log base 10. And if you want to write base 10, you can. Right? Remember, the log without a base is log base 10. And then 10 to the negative second divided by 10 to the negative 12th would be 10 to the positive 10th power. Right? Negative 2 minus negative 12 would be negative 2 plus 12, 10 to the 10th. And then 10 to what power is 10 to the 10th power? Well, this would just be 10. So this is 10 times 10, right, the log base 10 of 10 to the 10th power. 10 to what power is 10 to the 10th power? That's just 10. Right? And you could set up a little equation if you want, but this is 100. 100 decibels is the loudness level. Oops, sorry. 100 decibels. So back on the assignment, I'm putting 100. Yeah, so you just had to find that decibel level of sound formula in either your reading, or if you clicked on more instruction, you could have also seen the formula that they needed you to use. Yeah, let's continue on. Now we might come across other formulas that are necessary for other problems, but when we get to those, I'll just bring them up. All right, next question. All right, so another use logarithmic models in applications problem. So this one's about earthquake magnitude, earthquake intensity. So there's a totally different formula for that, right? Another model, and I have that written out somewhere. I'll bring that up. And again, that should either be in your reading, or you can click on more instruction and see what formulas are necessary for the problems you're working on. I don't expect you to memorize these. So in 2014, Chile experienced an intense earthquake with a magnitude of 8.2 on the Richter scale. In 2010, Haiti also experienced an intense earthquake that measured 7.0 on the Richter scale. Compare the intensities of the two earthquakes. Use a logarithmic model to solve. Round to the nearest whole number. Alright, so we have a multiple choice here. The intensity of the 2010 earthquake was about 16 times that of the 2004 earthquake. Well, not quite. I mean, the 2014 earthquake should be the more powerful one. So I'm going to say it's the second choice or the fourth choice, because they're saying the 2014 earthquake is 10 times, is more intense than the 2010 one, because like that has a higher value on the Richter scale. Well, anyway, so let me bring the question up along with some paper. Now the model being used here is this one. Let me put that piece of paper up, about earthquake intensity. And earthquake intensity is a simple one, a simple model. Again, you don't have to memorize this. You can find it in your reading, find it in the more instruction. We have r equals log of I. And again, this is log base 10, the common logarithm, where r is the magnitude, right, the value on the Richter scale, and I is the intensity of the shock wave, right, the intensity of the earthquake. So here's the 2014 quake, right, the 2014 quake in Chile. It was 8.2 on the Richter scale, right, so 8.2 is equal to r, the magnitude. And the 2010 earthquake in Haiti had a Richter scale magnitude of 7.0. So what I'm going to do is solve for I, solve for the intensity of both of these quakes. Alright, so for the first one from Chile, 2014, we have 8.2 equals, the log of I, and then solve for I. Now if you remember, this is equivalent. If I change to exponential form, we can solve for I. I'll just put change to exp form, exponential form. Remember, this is 10 base 10, 10 to the 8.2 power equals I. Alright, so the intensity of the Chilean quake in 2014 is 10 to the 8.2 power units, right, whatever the units of that are. And similarly for the 2010 quake in Haiti, we have the magnitude 7.0 is equal to the log of its intensity. Right. So I'll say this is IC for Chile, and I'll call this IH for Haiti. So the intensity of the Haitian earthquake was 10 to the 7th power. Right. And if you were to divide these, right, dividing gives me, the comparison. 10 to the 8.2 divided by 10 to the 7th is 10 to the 1.2 power, which if I round that to the nearest whole number, let me pull a calculator up. All right, 10 to the 1.2 power. It's about 16. All right, it's about 16 if I round to the nearest whole number. So this tells me, because I took a Chilean earthquake intensity over Haitian earthquake intensity, it tells me that the Chilean earthquake is about 16 times more intense. Right, the Chilean quake is about 16 times more intense. Than the Haitian earthquake. Right. And that's our answer, right? That's one of the choices. I mean, I think they say 2014 and 2010, but going back to the assignment, the intensity of the 2014 earthquake was about 16 times the intensity of the 2010 earthquake. So I hope all that made sense. Again, the model I used, that r equals the log of I, that was just something I found in reading, right, in the more instruction for this particular section. Right. Great. All right, next question. So you saw me just solve some logarithmic equations by changing the exponential form. And that's exactly what this objective is already about. Right? Solve a logarithmic equation by rewriting the equation in exponential form, which you should know how to do from section 10.3 part 1. So I'm not going to go into all that again. I'm just going to change it. I'm just going to go in and change it. So here we're given this equation. Then, now remember I said ln. That's log base e. Remember, this is the same as the log base e of x equals 5. Right? These mean the same thing. Now if we change this to exponential form, remember that would be e to the 5th power equals x. And that's solved for. Right? X is alone. So the natural log of e to the 5th is 5, and that works out. Because it's just e to what power equals e to the 5th power. Well, that would be the 5th power, right? It would be 5. So and this is what I'm entering, e to the 5th. Right? They don't ask us to round it or anything, so just enter it in exact form. X equals e to the 5th power. And that should be it. Great. All right, next question. There's another one. Solve a logarithmic equation by rewriting the equation in exponential form. This one I really don't have to, because the natural log of e to the 4x is just 4x. Right? Logs with a base, and then if the argument with that same base is inside, they kind of undo each other. But I'll write it out. Okay, so remember this natural log is base 8. So if I change this to exponential form, this would be base e. So this would be e to the 8th power equals the argument, equals e to the 4x. And then I can use that 1-to-1 property, right? Both sides have the same base to a power. The only way they're going to be equal is if those powers are equal. So if 8 equals 4x, and then dividing by 4 gives me x equals 2. And you can check it out. The natural log of e to the 8th is 8, right? E to the 8th would be e to the 8th. That works. So this is a good solution. So x equals 2. Easy enough. All right. Next question. So we have, once again, we're not asked to graph the whole thing. We're just asked to find certain inputs that would give me an output of 1 and -1 for this function. Now this is log base 13. So if I plug in 13, I'm getting 1, right? 13 comma 1. The log base 13, 13 to the 1st power would be 13. And then if I have y equals -1, 13 to the -1st power would be x. If I change to exponential form, so that'd be 1/13 for the input, giving me an output of -1. That's a very, very simple one there, just like earlier with the log base 10. Great. Again, please read through the answer explanations. All right, now this time it's log base 10, right? When there's no base written and it's just log, that's base 10. So I change this to exponential form. This will be 10 to the 2nd power equals 5x minus 5. Well, 10 to the 2nd, that's 100. Then adding 5 gives me 105 equals 5x. Then dividing by 5, x equals 21. And check it. If I put in 21 for x, this would be the log of 100. Log base 10 of 100 equals 2. And that's true because 10 squared equals 100. This works out. So that solution is 21. Great. Next. Alright, so one more. So again, x equals 3. I can see it right now, but I'll write it out. Alright, so that's this equation here. If I change to exponential form, remember this ln is the log base e. So that's e to the 6th power equals this e to the 2x inside. And now I can use the one-to-one property and say that, oh, the exponent, they both have the same base, so their exponents, their powers must be the same, and then dividing by 2 gives me x equals 3. Right. And you can check it if you want, but it works. Alright, so x equals 3. Alright, and that should be it for that objective. Alright, and then the graph thing again, they're just giving us a logarithm, and we just have to fill in the x coordinates to certain points. If y is 1, you'd have 1 equals the log base 1/9 of x. To solve for x, I change to exponential form. X would be 1/9 to the first, or just 1/9. So this graph would have the point 1/9, comma 1. And then if y were -1, you'd have x equals 1/9 to the negative first. Now 1/9 to the -1 would be positive 9. So you'd have 9 comma -1, and this would be one of those decreasing functions, right? The base is less than 1, and you could graph it if you wish, but I'm just going to fill in those points. Right, these should be pretty easy. All right, and then one more like this. So it's y equals log base 17 of x. So if y were 1, x would be 17 to the first, or just 17. So you have the point 17 comma 1 on the graph. And if y were -1, x would be 17 to the negative first, or 1/17. So you'd have the point 1/17 comma -1 on the graph as well. Very, very simple. Alright, and then finally, we got 2 more questions using models here. Alright, so we're back to the earthquake intensity. So this is very similar to the one earlier with the Chilean one and the Haitian one, but this time it's an Indonesian earthquake from 2012 and a Ugandan earthquake from 1952. One has a magnitude of 8.6, the other 6.5. We just have to compare the intensities. Right. Now the larger magnitude earthquake was the 2012 earthquake, right? So it's either the first or second one, right? The 2012 earthquake was more intense than the 1952 one, so it's either the first or second choice. All right, so let me pull up that paper with the. Here was the earthquake intensity model. Right? R equals log of I. Again, the 2012 quake, R, the magnitude was 8.6. Alright, so we have 8.6 equals the log of I. Alright, and I'll call this I1, right, just because it's for the first earthquake I'm looking at. And if you solve for I1, it's going to be 10 to the 8.6, whatever that is, right? 10 to the 8.6 power. And then for the 1952 quake in Uganda, the magnitude was 6.5 on the Richter scale. So we have 6.5 equals the log of I, and I'll call this I2 because it's a separate I, a different intensity. And if you solve for I2, it would be 10 to the 6.5 power. And then we'll take their ratio. We'll take the intensity from 2012's quake divided by the intensity from the 1952 quake. So 10 to the 8.6 divided by 10 to the 6.5 would be 10 to the 2.1 power. Which is going to be a little bit more than 100. All right, now I'll pull up a calculator again. (10 raised to the 2.1 power). So almost 126. Almost 126 there if you were to round to the nearest whole number. Okay, so this tells me that the quake from 2012 is about 126 times the intensity of the quake from 1952, and that's what I will answer. And that was the first choice here. Great. All right, and once again, please read through your answer explanations, and we should have just one more question involving applications. And it's basically the same thing. All right. So, I mean, I had the decibel level of sound formula up earlier, and we're working with this earthquake intensity formula right now. Just know that you might see some other questions involving different models, right? I would just click on more instruction just to see what model they're talking about, if I were you. All right, so this one here, we have a 1964 quake from the United States, has a magnitude of 9.2. And a 2008 quake from China that had a magnitude of 7.9, and we're asked to compare the intensities again. Now, because the 64 quake had a larger magnitude, I'm going to say the intensity of the 64 quake was larger than the 2008 quake, so it's either the first one or the fourth choice. So it's either, but now we have to figure out, is it 20 times the intensity or 30 times? And that's where that ratio will come in. All right, so once again, the earthquake intensity model. In the 1964 quake, the magnitude was 9.2. So we have 9.2 equals the log base 10 of, again, I'll call this I1, the first intensity. And if you solve this for I1, you get I1, the intensity of this quake was, 10 to the 9.2 units, whatever units of intensity are. And then for the 2008 quake in China, right, the Richter scale measurement, the magnitude was 7.9. So we have 7.9 equals the log base 10 of intensity 2, right, I2, and then solving this for I2, get 10 to the 7.9. And then look at the ratio of these two intensities. So again, I'm taking the larger one over the smaller one. So we have 10 to the 9.2, the 1964 quake intensity, divided by 10 to the 7.9, right, the 2008 quake intensity. And that's 10 to the 1.3 power. And I'm going to put that into a calculator. So pulling the calculator back up. 10 raised to the 1.3 power, about 20. All right, about 20. So looks to me like the quake from 1964 is about 20 times the intensity as the quake from 2008. And that was this fourth choice here. Alright, so once again, just because I saw 3 earthquake problems doesn't mean you are. Right? You might see a bunch of decibel level problems or other types of problems. If you're unfamiliar with the model to use, just click on more instruction or go to your openstacks.org intermediate algebra text, section 10.3, and read through that. Alright, and that should be it for this version of this assignment. As I said at the top of the video, the questions I saw here are not necessarily going to be the same questions you see when you work on the assignment yourself. But, the objectives are the same. The types of questions should be similar. So I'm hoping that watching me go through these, I think it was 12 questions here in this video, hopefully these help you in some way when you're working on the assignment yourself. And thank you very much for watching.